Hi everybody. In this video we are going to discuss the basics of an inductor and we are going to look into the voltage and current relationship. Well, let's start off with the inductor model, and to start with a model we start with some physics. Suppose we have a wire and through that wire a current flows. By means of that current, magnetic field lines are generated across that wire over here, and the higher the current will be, the more magnetic field lines will be generated. So how can we determine the direction of these magnetic field lines? Well, we can do that by using the right hand rule, and in that right hand rule we put the thumb into the direction of the current and all the other fingers express the direction of the magnetic field line. So that is expressed over here. But when we rearrange that wire and we rearrange it in this form, so we wind them, rewind them like a coil, we get a so-called inductor. And in that inductor, the magnetic field lines are concentrated. They are concentrated like the dashed purple lines indicate. Well, some parameters about an inductor. Well, what is important? The inducted area is the area over here, which is the purple or red area. And then inductor has n windings, and the number of n is expressed over here, which is in this example the number of 4. And we have the length of the inductor, and that is the length L. And all these parameters are necessary to be able to calculate the value of that inductor, which we are going to call the inductor value or the L, but that's in a couple of minutes. Suppose we connect that inductor to a current source, then a current will flow and that current will yield to a voltage across the inductor terminals, but we will express that in a couple of minutes. A couple of other physics expressions which are important to understand what's happening in that inductor. First of all, we are going to determine the parameter flux, which is indicated over here, and that flux is equal to B times A, and B are the number of magnetic field lines which are perpendicular to the area A. Then we get the magnetic flux. Based on this scheme, based on this circuit diagram, we can define a symbol for inductor, and the symbol for inductor is this symbol. And the most important parameter, as I expressed earlier, is the parameter L, which is the inductance value. And as I said, when a current flows through that inductor, a voltage across the inductance terminals is generated, and we call that UL. Now that inductance value, this L, we can calculate it by this formula. L is mu times n squared times A over L. What does that mean? L is mu, which is the magnetic permeability, which is a physical factor about the material around this coil has been wired. And it could be air, but it could also be an iron core, and then we have to use the value for mu, the value of iron. N is the number of windings. 4 in this example. A was the cross section, the area over here, and L is the length of this inductor. L is also equal to the flux, which is defined over here, divided by IL, the current through this inductor. And the unit of inductance is Henry. It's called to a French guy, Henry. So that's the unit of inductance. Well, when we have this, then we can generate the most important formula for an inductor, which says that U, the voltage across the inductor terminals, is equal to L, the inductor value, times di dt, times the derivative of the current flowing through the inductor. We can also state it's L times the change of the inductor current. Well, some other things when we are making circuit diagram, or we are working with a couple of coils or inductors in one circuit, then we have to know the rules about parallel and series connection. When we put two or more inductors in parallel, we can express the replacement inductance value, and it's expressed in this way: 1 over LV, so the inverse of the replacement inductance, is 1 over L1 plus L1 over L2. So the replacement inductance value, the inverse of it, is equal to the inverse of L1 plus the inverse of L2. And of course, when we put more inductors in parallel, we have to add all the inverse inductance values to it. So this resembles the same situation as what we do when we put resistors in parallel. The same thing happens when we put inductors in series. Then we can do the same thing as with resistors. We can define the replacement inductance value, which is equal to L1, the inductance value of the first inductor, plus L2 plus, and so on till the last inductor value. So also this is also the same with resistors. Well, now let's look to that current voltage relationship. We have expressed in an earlier sheet that UL is L times di dt, which is caused by the fact that UL is equal to the change of magnetic um, um, flux, so the change of flux, so dV dt. But this is the most important one. U is L times di dt. Suppose we have a situation in which we connect a voltage source to an inductor. And when we do that, a current will flow, and that current will create an inductor voltage across the inductor terminals. When we express the voltage and when we want to calculate the current, we can based on this expression, get an expression for the inductor current. Well, U over L, when we divide both sides of the equation by L, gives us the change of inductor current, the IDT. So then I, the inductor current, is equal to 1 over L times the integral of the voltage to time. So I is 1 over L times the integral of the voltage. Well, integrating is in a graphical way the same thing as calculating the area underneath the curve. In this situation, the voltage applied to the inductor is a constant voltage, as expressed over here. So when we have a constant voltage, then we get the integral is the running area underneath this curve, and the running area underneath this curve gives us a linear relationship for the current, because when time increases by a factor of 2, then this area is increased by a factor of 2, so we get that linear relationship, which we can also define by using this equation, which states that 1 over L times the integral of constant value, which is U times T. And that's expressed over here. So in this expression, or in this example with the constant voltage, I is equal to the constant voltage times T. So this is the running area underneath this curve divided by L, so divided by the inductor value. So let's work this out with an example. And in this example, we have a constant voltage, but it changes at some points changes its polarity. It switches from a constant positive value to a negative value. And the inductor value is 25 millihenry. So 25 times 10 to the power of minus 3 Henry. So how will the current look like? Well, we are going to use this expression. U is L times the IDT, and we have seen that we can put that in another way. We can also say that I is 1 over L times the integral of the voltage U. So it's the running area underneath the curve divided by the inductor value. Well, what happens? The current will increase linearly at what we have seen in the previous slide, and at this point the maximum value of that running area is 10 times 2.5 milliseconds, which is 25 milli, so 25 times 10 to the power of minus 3. But we have to divide it by the L value, which is 25 millihenry, so we get 25 divided by 25, which gives us an amplitude of 1 amp, 1 ampere. At this point, my voltage switches to a negative value, and we get more and more negative area, and that negative area causes the current to decrease also linearly, and at this point 7.5 milliseconds. The total of negative area is 7.5 milliseconds minus 2.5 milliseconds, which equals 5 milliseconds, times minus 10 is equal to minus 50 times 10 to the power of minus 3. We have to divide that by 25 millihenry, so we get a current drop of minus 2 amps. But we started off at 1 amp. 1 amp minus 2 yields minus 1 amp at this point. And it goes linearly because this is a constant voltage. And here in the middle, then the negative area over here equals the positive area over here, so then the current at this point is 0 amps. Here the voltage is positive again, so my current starts to rise, etc. So this triangle form is caused by the fact that this voltage is constant using this expression. Now let's look to a real AC situation in which we add a AC current source to that inductor. And the AC current source is expressed by this equation. I is I top times the sine of omega, which is the angular frequency of the sine wave from the current, times t. Because it's an inductor, still this expression is valid. U is L times di dt. What we see is the following in this situation. Suppose this blue sine is the current, which is expressed over here. Then we can calculate the voltage across the inductor terminals by using this equation, which states that U is L times the derivative of that current. And the current is a sine wave, so the derivative of a sine wave is a cosine wave. So the current has a cosine wave, which means that the top of the current the top of the voltage, so the red graph, is earlier than the top of the current, which is the blue graph. So the voltage across the terminals of the inductor are earlier than the top of the current. So we can say that in this situation, the voltage leads the current. We can also say the current lags the voltage. So that is also caused by this expression. What we can also do is we can put these in a so-called vector diagram or a phasor diagram, in which we only express the amplitude of the voltage and the amplitude of the current. Suppose we put the voltage on the horizontal axis over here, so the top value is put over here. Then we have to put the current on the negative y-axis, and that is because the current lags the voltage, and it lags the voltage by 90 degrees, as we can see over here. Again, because the current is a sine wave and the voltage is a cosine wave. So the current lags the voltage by 90 degrees. This is defined as plus 90 degrees. This is defined as minus 90 degrees. And of course, in radians is minus 0.5 pi. So again, current lags voltage for an inductor, or we can say voltage leads the current. And another important thing what we have learned in this video is that we can calculate the voltage across the terminals of an inductor by using this expression, U is L times di dt. Thank you for watching and see you next time.